Hi, I'm Hyungjin Chung. I will be presenting our work solving 3D inverse problems using pre-trained 2D diffusion models, a joint work with Tohun, Mike, Mark, and John. The main goal of this work is to solve 3D inverse problems, especially focusing on the problems arising in medical imaging. Specifically, we propose a general inverse problem solver where our same algorithm can be applied in the same fashion. Here, we show a representative result of our proposed method, dubbed diffusion MBIR. As can be seen in the figure, from very sparse measurements, our algorithm is able to reconstruct a coherent 3D volume using a diffusion model trained only on 2D slices. We also show that we can apply the same algorithm to different problems, resulting in reconstructions that are faithful to the measurement, even in the most extreme conditions. Moreover, we also notice that the proposed method is very robust to distribution shifts, being able to reconstruct a completely different phantom object with a diffusion prior trained on human torso. Our method is built on diffusion models. Diffusion model is a class of generative model that generates data by iterative denoising. The training of such generative process boils down to training a residual denoiser that learns to denoise an image given noisy realizations of different magnitudes. Usually, the trainable network is set to a unit with a time-dependent conditioning scheme. On the other hand, we are interested in solving inverse problems in this work, where the aim is to recover the clean image X from the noisy corrupted measurement Y. Due to the opposingness of the problem, there exists infinitely many solutions that are feasible, and hence it is our job is to properly incorporate the prior of the data distribution in order to achieve a good estimate. Over the recent years, there has been continuous growth in the interest in using diffusion models as generative priors to solve inverse problems in imaging, thanks to their amazing sample quality and modularity of the inference procedure. In essence, you can leverage a pre-trained denoiser as is, and slightly modify the inference procedure to achieve a posterior sample that matches the measurement condition. This scheme can also be interpreted as a method of Bayesian inference, as the denoiser in the diffusion model can also be thought of as the score function, which is the gradient of the log prior. Hence, we can achieve posterior sampling by incorporating the data likelihood into the denoising scheme. While many different works were proposed as general solvers, scaling to noisy and nonlinear problems, it should be noted that most methods were heavily focused on 2D image and restoration problems. And the same applies to methods tailored for medical imaging inverse problems. However, in many practical situations, it is important that one can provide a solution to a 3D inverse problem that is coherent across the full volume. This includes sparse view and limited CT problems imaging human body, and 3D MRI brain imaging, where the measurement is acquired in an accelerated fashion. Now, simply scaling diffusion model-based inverse problem solvers to 3D is hard due to memory and computation issues, as diffusion models in 2D are already quite heavy as the Markov chain stays in the data dimension. One could try to leverage more compact representations, but it will often be infeasible for cases such as medical imaging inverse problems, where visualizing the interior is of absolute necessity. Thus, in this work, we aim to devise a 3D inverse problem solver that solely relies on 2D diffusion models. Let us revisit the posterior formulation, where it can be represented as the product of the prior and the likelihood, where likelihood is given from the measurements model. Our proposal is to model the prior as a factored prior, where it is split into the prior that operates in the XY direction, and the remaining prior operates solely on the Z direction. Here, we are going to leverage the generative diffusion prior using the pre-trained diffusion model on 2D slices, as the prior operating on the XY dimension. For the prior on the Z direction, we will use the total variation prior, which effectively models the smoothness across the slices. Our intuition here is that diffusion prior already has rich information about the data distribution, and simply augmenting this with a conventional model-based prior that imposes coherency will suffice to induce a proper reconstruction. In order to do so, we propose the following sampling scheme. We leave the usual denoising steps as in the reverse diffusion steps. Then, after a single step of denoising, we propose to solve the following optimization problem, where the problem is simply a regularized least squares that tries to minimize the L1 norm of the finite difference in the Z direction. Dissecting each component, the diffusion prior is naturally incorporated in the denoising step, and the likelihood and the model-based prior are incorporated in the optimization steps. Visually speaking, as the diffusion model denoising steps operate in 2D, they will be independently denoised. Then, ADM-MTV step will be run in the whole volume jointly. However, applying these optimization steps at every iteration of denoising will result in sampling steps that are too slow. In order to yield a fast sampler, we propose to share the primal and dual variables of the ADMM optimization steps across the whole reverse diffusion sampling steps. When we implement the algorithm as such, we are able to achieve fast convergence with only a single iteration of ADMM and a single iteration of conjugate gradient between each denoising step. Applying diffusion MBIR, our newly proposed solver, to sparse view CT with only 8 view measurements, we are able to achieve coherent reconstructions across the full volume. The same applies to limited angle tomography and compressed sensing MRI, proving the generality of our approach. We also compare our method quantitatively to other state-of-the-art methods, including diffusion model-based inverse problem solvers, supervised learning methods, and model-based reconstruction methods. In almost all metrics, we outperform methods that are considered prior art. What's more, we also show that our method has high generalization capacity. For example, when applying a diffusion model trained on human torso to a phantom containing random spheres, diffusion MBIR produces a high-fidelity reconstruction from only 8 view sparse measurements. Thank you for listening. If you're interested, please check out the paper and the code.